All right, so we've looked at hidden Markov models and we've sort of motivated why one might use these for part-of-speech tagging. But we haven't really talked about how to train them or how to use them to actually do this task. And so let's talk about training first. And so in the last video, we talked that we discussed that there were three different probability distributions that we needed estimates of. We had the transition probability, we had the emission probability, and then we had this initial state probability, which is sort of that special case of the transitions. And how we're going to do this is actually not very sophisticated. We're going to go back to n-gram models that we learned about earlier in the class, and we're going to apply a very similar technique here. Right? So if you look at the slide, you can see that we go state A to state B, and then back to A, and then B, A, B, A, B. And if I asked you what's the next state going to be, undoubtedly all of you are thinking, we're going to go back to state A. And you can imagine that these n-gram model type of count-based models are going to capture this very well, right? We're going to say, how many times did I see state A? And of those times, how many times did I transition to state B in the next state? And if you look at the training example on the screen, you'd say, well, every time I'm in state A, all four of them, every single time, I went to state B in the next step. And similarly, every time I see state B, I transition back to state A in the next time step. And just counting the instances in the training set, and then just doing the ratio of how often it happened divided by how often did I see the context, will give you the transition probability. And we'll do exactly the same thing for emissions. We'll say, well, when I'm in state A, how often do I output red? How often do I output green? And this little toy example that we've gone back to, similar to the one we initially used to discuss hidden Markov models, we're just going to use it as a little toy. And there's nothing new or fundamentally different about increasing the cardinality to all the parts of speech or all the words in the language, but it's just easier to reason about when you only have two states and two types of things that could be emitted. And then you can take that intuition and apply it in sort of the bigger space. All right, so how do we do this? So imagine this is our only training example, right? So we have a single training example, which you would never do, but for the purposes of the slides and working through this, let's pretend we have a single training example. Here it is on the bottom of the slide. Let's see if we can figure out these probability distributions. And so the first one we want to do here is that initial state probability. So if we look at our training example and we look at y0, and that's this A over here on the far left, upper left corner, we say, well, of all of the training examples that we have, 100% of them start with the state A, right? We're 1 for 1. So 1 divided by 1 is 1.0, and so then we will say that the probability of y0 being A is 1.0. And of course, once you have that one, the other one's really easy. I mean, you also know that you have no training examples starting with a B, so you could just write a 0, but you also know that the probabilities have to add up to 1. And that's useful when doing some of these calculations, just to know I have a probability distribution. If I know one answer, I can figure the other one out because it's just 1 minus what you have so far. And all right, so P of y0 is B. And so the initial state we're done with. Let's look at transition. So this is the state transition probability distribution. So we're going to look at when I'm in each state, either A or B. What's the probability that I stay in that state? What's the probability I transition? So the first one, let's do P of yi is equal to A given yi minus 1 is B. So this basically says if I'm in state B, right, so y minus 1 is B, what's the probability I'm going to transition out of B and into A for the next step? All right, so what do we do here? We need to count up how many times did we see B? How many times were we in state B? So we were in state B 1 time, 2 times, 3 times. We'll ignore the one at the end because we actually don't know what it transitions to. So we'll just look at the 3, 1, 2, and 3. And how often of those 3 times we're in state B, how often do we go to A? So let's look. So here we are at B, where we transition to A. In this B, we transition to A. In this final B, we also transition to A. So all 3 of our examples, we are in state B, we transition to A. So what's the probability of that? Well, that's 100%, right? So 100% of the time we're in state B, we transition to A. And so then the question is, well, what's the probability I go to state B given I'm already in state B? Well, that's 0, right? Because every time we're in B, we go to A. We never stay in B. So 100% of the mass is on this transition from B to A. And similarly, because of the AB, AB, AB pattern, that's going to be true the other way around. Anytime I'm in A, I'm going to go to B, right? And so these are both 100%. Now in practice, they're never 100%, but this will keep the math easier for the rest of the example here. All right, so we're done initial state and transition. The only ones we have left are the emission probabilities. These are slightly more interesting, so let's just take a quick look. So if I'm in state A, what kind of emission do I tend to do? And so the emission probabilities depend only on the current state. So let's take a look. How many A's do we have? We have 1A, 2 A's, 3 A's, 4 A's, and every single time we output a red. So what's the probability of red given being in state A? 100%. All right, what about B's? So B's are a bit different, right? So this B emits a green, that B emits a red, and then these two guys over here also emit greens. So we have 3 greens and 1 red. So what's the probability of red given that we're in state B? Well, we were in state B 4 times, and we saw 1 red, and so that's a quarter. And then similarly, what's the probability of emission of green given that I'm in state B? Well, that's the number of greens that are emitted divided by the number of times I was in state B. So that's 3 divided by the 4 times I was in B. So that's 3/4, which you'd expect because those two need to add up to 1. All right, so here we are. We have now estimates of all the parameters in our hidden Markov model. We have the initial state, the transition, and the emission. And so assuming we have all of these, let's say we want to score a sequence. And this is what we're going to do when we try and figure out the part of speech tags. We're going to be given the X's, right? So we're going to be given the reds and greens, and we're going to try and figure out what the most likely set of tags in that sequence of Y's, the hidden states, is going to be. Or to put it a different way, we need a way of scoring a sequence of Y's. So we want to know, well, what is the probability of this assignment to Y0, Y1, Y2, Y3, ... given the observations x0, x1, x2, ... And to do this, we can just apply Bayes' rule, as you can see on the slide here, right? We just take the joint probability divided by the probability of the right-hand side. And now, as it turns out, the right-hand side here is just the emissions, so these are the things you've observed. And this probability doesn't depend at all on the part of speech or the states that you're going to assign to those hidden variables. And so you can actually just ignore it, right? So if you maximize the numerator, you're going to maximize this thing on the left-hand side because the denominator is just a constant. And critically, it's always positive. So it's a positive constant between 0 and 1 in the denominator here. And because of that, if you make the more you drive the numerator higher, the more this probability on the left is going to go up. And so in general here, we're going to just really try and understand this joint probability up in the numerator and use it to score sequences. All right. So that's a lot of talking about what we're going to do. Let's actually try it with the transition probabilities and the emission probabilities that we just used or we just trained on the previous slide. So here we are. So let's say we have this little fragment ABA. And the A emits a red, the B emits a green, and the A emits another red, and we want to score this joint assignment to all these variables. So what is the probability that Y0 is A, Y1 is B, Y2 is A, and then the emissions are red, green, red. All right. So how do we do that? So first we need Y0 to be A. So what is that? That is probability of Y0 equals A, that's this value here, so that captures this state variable. And then we need to capture its emission, right? So what's the probability of red given I'm in state A, right? So that's the second term. And then we continue on with the second step in the sequence. So here we're going to find the probability of Y1 being B, given that Y0 is A. And I just want to point out here that what it doesn't depend on is x0, right? That's the Markov assumption that we're making here, is that B depends on nothing. It's conditionally independent of everything except for y0. So y1 only depends on y0 and nothing else. And so you could absolutely write all the rest of the variables on the right-hand side of the conditioning bar, but if you recall from the review of probability, if they're conditionally independent, then you can simply drop them off the right-hand side of that conditioning bar. All right, and so we continue on here. So here's the emission in the first time step, and then the transition to y2, and then finally the emission of x2. And this gets you the probability, this joint probability we've decomposed using this Markov assumption that all these dependencies across all of these other terms, other than these little pairwise dependencies, basically don't matter. It's common to write these with square brackets around pairs of terms. And you can see here each set of terms in these square brackets correspond to one step in the sequence. All right, so let's plug the numbers in. And so you can see I've done that, and you say, the probability of this is 0.75, which is not surprising given the number of 1.0s throughout the tables here. All right, so then the question is, all right, so we've now managed to score a sequence. Of course, what we're actually doing in the part of speech tagging is not trying to score a sequence, it's to figure out the best sequence. And so what can one do? The most brute force, simplest thing one can do is just enumerate all the possible joint assignments to those hidden variables, score all of them, and then just pick the best, right? So you can imagine, and maybe you want to pause the video and just see if you can figure these out yourself, but imagine you see the sequence red, red, green, red, and you want to figure out, well, what is the most likely assignment to these four hidden states, given these transition tables that we built up on a slide a few back. Now I made one change here. I changed the initial state probabilities so that it doesn't always start on A, so it's going to be, I changed initial states to be 50-50 between A and B, but I left everything else the same. And see if you can figure out what the most likely assignment of states are here to these hidden variables. All right, so if you've done that, you'll see that actually the only sequence that really makes a lot of sense given the probabilities that are here on the slide is this one here. So we start on B and then we go A, B, A. And we know this because, intuitively, because A's always go to B's and B's always goes to A's, so you know it's either got to be A, B, A, B or B, A, B, A, and A never outputs a green, so that B had better be in the third position. But you can see this if you actually try the other probabilities and just try scoring them just like we did on the previous slide, you'll get zeros for everything except for this one. And this one, as you can see from my math here at the bottom of the slide, you get 87.5 is the likelihood here. All right.